Hello and welcome to Learning Trees Data Wrangling with Python webinar. Today's presentation will be broadcast via voice over IP. There will be a 15-minute Q&A session at the end of the presentation, so please submit any questions that you may have through the chat pod. Presenting today's webinar is Chris Mawada. He has been an author and instructor for Learning Tree for 20 years. Last week was his anniversary. He is an expert in all things big data and data science. I will now turn it over to Chris.
Good afternoon, everybody, and welcome to the seminar. Thanks, Amy, for the introduction. So today I want to discuss with you, why does Python have such a high regard among data scientists? Among all the languages we have to choose from, why would we choose Python? So I want to point out some of the nice and convenient things you get when you use Python. And let's start by looking at data science itself. So when you perform some data science, you're really starting from some data, which is of course the data in data science, and you want to end up with some kind of data-driven decision, some insight, some information that you would not have had otherwise. So the story starts from gathering data. You will get data from various places. Think of getting data from social media, getting data from logs, which really act very much like a diary of what your system has been doing. Maybe from some website which publishes things every so often. Perhaps it's a continuous kind of thing like trade data or data from Internet of Things devices. You could have data in-house. We all have relational databases. Many have NoSQL databases. You have other big data systems like Hadoop, etc. But typically, even after you've decided that this is the data that is going to provide me with enough information to predict what I'm trying to predict, you're still going to find that it is not in the format you want to feed to your models. So a lot of time is spent doing what we refer to as data wrangling, which is taking that raw data and getting it to the format that would allow you to do some modeling with it, do some prediction with it. Maybe you're trying to prescribe a course of action. So some of it will be structuring the data. It might be data with very little structure. Some of it might be dealing with imperfections. Maybe some of the records have entries that are missing. It could be that your particular model does not like outliers, so we need to take care of those. If it is even less structured to start with, think of things like text. You need to do a lot of work to go from text to numbers. You need to parse the text. You need to figure out a way to represent what is in that text using vectors. Maybe you're parsing JSON documents. Maybe you're parsing XML documents. Joining data. In many cases, you'll find that your data comes from multiple different data sources. Okay, so once you've got the data in the structure you want, then you can think of feeding it to some kind of processing software. Maybe you're building a model, so you decide, am I going to do some classification? Do I need to do clustering? Am I trying to do image recognition? Is it natural language processing? All kinds of different models that one might want to create out of this data. But the end product, the thing that you're after, what makes all this worthwhile, is at the end of the day, you're going to have some insights, and typically these insights are going to be consumed by somebody other than you. So you have some stakeholders. It could be it's your customers who need some information. It could be people within your organization who are making decisions. It could be employees who are out in the field who need to figure out the best strategy to do something. So your deliverable, if you like, is going to be perhaps a report, perhaps it's going to be a presentation to your management, to other stakeholders, or it could be a program that runs in production and continuously gives you insights as to what is the sentiment of your customers right now, or what should be your strategy based on the current environment. Which devices should you repair based on the sensor data coming from them. And in many cases, I dare say almost all cases, there will be some visualization involved as you create dashboards and other kinds of reporting tools. Now, the section over here where you gather data and you try to get it into the form that is ready for processing, that takes up a large chunk of the time of a data scientist. People estimate about 60% of their time is spent on just getting ready to train their models and to get the actual answers. So that part, the data wrangling, is extremely important. Now, the model building, model evaluation, creation of reports, that is also very important, and we shall make it the business of another webinar that is coming up. But today I want to talk mainly about the data wrangling, and in particular, why Python? Because there are many languages, as you will know, but why is Python the favorite? Okay, so my background is in pure mathematics, and my initial adventures in artificial intelligence was when I was still a PhD student, and one of my advisors was working on a little artificial intelligence project. We were doing symbolic manipulation. Remember those little calculators that TI had that could do differential equations and those kinds of things? Essentially, TI bought my advisor's software, and that's how I got into it. In those days, the language of choice was Lisp. So what has Python got that makes it so suitable? Well, Python is an object-oriented language, and it is also a functional language, which becomes useful because when you try to parcel out work to multiple machines, each one doing a piece of the work, it is easier to send the function to the machine than to have the data come to the function. And so functional languages are becoming very important because it's so easy to direct another machine to do some work. You send the function over. Okay, so my first look at Python was quite a while ago, and it wasn't a very interesting language to me. It was very useful to people who are doing scripting. Most of you will notice that in your Linux systems, really Python is the glue that holds things together. Before, Perl also was really the prominent one for that kind of role, but now you'll find Python is really what glues the various parts of your Linux system together. Or to put it another way, if you mess up your Python on your Linux system, you've really got a problem. So I didn't think of it as a language to do artificial intelligence, a language to do machine learning, data science, until they brought up a library called NumPy, and there's a sister library called Pandas. The big deal with NumPy is it gives you multidimensional arrays. And that's a big deal because a lot of what you do in data science is actually linear algebra. Everything has to be represented as numbers. Well, you know that computers only understand numbers, including things like free-flowing text has to become numbers. Otherwise, you can't really apply any meaningful logic to that data. So NumPy gives you multi-dimensional arrays. Not only that, it gives you functions that you can apply to those arrays. What kinds of functions? Well, functions that do standard linear algebra, multiplying matrices, finding determinants, finding inverses, finding eigenvalues. The kinds of things which before were only in scientific languages. So at the time I was messing with Lisp, there were a few other things like Mathematica, like KML, like MATLAB. Those were purely scientific, and they wouldn't venture into the enterprise world. And then on the other side, we had the C++, and Java was not yet around at that time. So this gives you a general purpose language that does have those capabilities. Then on top of that, people wrote really nice tools for machine learning. In particular, there are libraries like SciPy, that's scientific Python, scikit-learn. Those have a lot of the machine learning algorithms that we like to use. PyTorch, which has a lot of the neural network kind of work we like to do. And there are others, things like Keras, things like TensorFlow. Essentially, in the data science world, if you know Python, everybody will accommodate you. You will have a tool that you can use. The second problem that Python had, which made me not so interested at first, was the fact that it didn't scale very well. Python natively is single-threaded. And so if you're going to do things that are very data thirsty, things like training large amounts, models with large amounts of data, you need to be able to do things in parallel. But what Python does very well is to piggyback on other software. So when you want highly distributed processing, you'd use things like PySpark, which allows Python to run on top of Spark, and you write your code in Python, and Spark takes care of distributing it so that you can use very many CPUs, you can be drawing data from very many hard drives, and you can do as much as you can in parallel. So that problem got solved. And then the other thing that is very nice about Python, again, the fact that it is not shy about piggybacking on other languages, is that although Python itself is an interpreted language, it will happily call languages that are significantly faster, like C++, like Fortran in the background, so you don't have to go and learn those languages. You write your code in Python, and transparent to you, the code is actually running some C++ routines in the background. So what I'm hoping to convince you today is that there's a lot to be gained by learning Python, especially if you're going to go into data wrangling. And in another seminar, I'll talk about how Python is also really good when you do the actual modeling. Okay, so you take your first look at Python and you say, well, this is a language like any other. It is a language with the usual suspects as far as types go. There is a text type. Every language worth its salt has some kind of string type, numerical types, integers, floating point numbers. It is interesting that Python has complex numbers as native. Most languages need you to essentially do a hack to make complex number mathematics work. Sequence types, again, any language you want will have lists of some kind, tuples, ranges. Dictionaries are like your hash tables, so again, no surprise. Let me just say that the standard primitive types, if you like, are what you would expect. What you want for something to be interesting to a data scientist is to be able to do the mathematics behind data science conveniently. And essentially, data science sits on top of a lot of statistics, a lot of linear algebra, differential calculus, and then also, for us humans, we need to be able to visualize stuff so that we can get a feel for large amounts of data without going crazy. Most of us can't eyeball more than a few hundred lines of a few hundred records without our eyes glazing over. So these capabilities come in with external Python libraries. And so what you have is NumPy especially made the mathematicians sit up and say, this thing is now interesting. Just like you have engineers swear by Fortran, now it became the place to go if you wanted to do anything in terms of high-dimensional matrices. Okay, so NumPy is the fundamental package if you're going to do any scientific computing in Python. And the multidimensional arrays, as I mentioned, are critical because a lot of what we do inside, those of you who've been looking at things like neural networks, every place you look, it is, here's a weight matrix, here is some kind of vector, multiply them together. So matrix multiplication is, as common as arithmetic would be in a standard program. So you get these sophisticated mathematical functions that you really don't want to write yourself, and in the background, wherever it is convenient, Python will call C code, C++ code, Fortran code. Okay, so the other thing, of course, apart from the linear algebra, Fourier transforms, these are extremely important in things like signal processing, in things like finding the boundaries of an image. So those come in as part of the deal. Statistical functions, you want a good random number generator if you're going to be building simulations of phenomena you're studying. So this is what this is a 2D NumPy array would look like. And what I want to do is to show you why this is not as primitive as, say, an array in Java, which is just a box with really nothing much. You know, if you have an array in Java, you can ask how many rows, how many columns it has. That's about it. But take a look at the Python version. And for the demos, I'm going to use my Google Drive. What I would recommend if you're starting out and you don't want to have to install Python on your own, if you have an account with Google Drive, they have a feature called Google Colab. Actually, they call it Collaboratory, but short is Colab. And in there, you can create a document and just treat it as a Python document, as Python source code. So let me show you a little bit of NumPy just to get you a feel of what this thing gives you. Okay, so this is how you start up with Google Colab. Essentially, you just have your file there and you open it in Colab. So there's my file. And you can see at the top I'm importing NumPy. The as NP means I'm using NP as the alias just to make things short. So let me import it. And let's take a look at some basic matrix algebra just to convince you that this thing is really nice. So I'm going to start off with just a long list of numbers. So A range means 0, 1, 2, 3, 4, all the way up to 23. So it looks like that. And I can just ask NumPy to reshape it so that it is 3 rows by 8. So here we go. So reshaping your matrices is just a one-liner. Let me create a second one. So this time I'm going 0 to 48, but in jumps of 2. So remember the last number isn't included. So it is 0, 2, 4, 6 up to 46. So there's 46. And I can then reshape this one. So now I've got 2 arrays. I called the other one array 1. I'll call this one array 2. I have 2 arrays and both of them are 3 by 8, which means I can do operations on them. For instance, maybe I want to add array 1 to array 2. Now, in a standard language, think of your C++, think of your Java, you would say, well, I'm going to have a loop that goes, take this one plus that one, take that one plus that one. In NumPy, it is just array 1 plus array 2, you're done. In other words, it understands the addition of arrays as an operation. Now, in the background, of course, it is running what you would have written, but why would you write something that is already built in? So here we have, I'll just pick a few numbers. So see the 14 plus the 28, and there you have the 42, and it's done the same thing for all of the entries. How about something more matrix-like? For instance, finding the transpose of a matrix. So this is my array 2. The transpose should be, sideways with the rows becoming columns, the columns becoming rows. And all you do is to say transpose of array 2. Let's call it array 3. And there you have it. So once again, things that would have had me create an array and then plug things in correctly, they become pretty straightforward. Here's a matrix product. So we've got this guy, and we've got these that are 3 by 8. So I should be able to multiply them actually both ways. So here I'm finding the product, array 1 and array 2. And here's the product, array 3 times array 1. I can do either one. Actually, I decided to do both. And you can see over here we have the product one way, and over here we have the product the other way. Now notice, if you're doing a matrix product, you remember that thing that you had way back in school. Let me remind you. Remember when you did things like this? You do things like this, right? Right? It was really a double loop. Well, now it is just a single liner, A1 dot A2. There you go. Let's take a look at maybe functions that are not built in, but you want to apply to every row, maybe to every column of your array. So remember, Python is function oriented. So I defined a little function here. What it does is it takes A, which is going to be a list, and A of 0, as you can imagine, is the first element of that list. A of -1 is actually the last element. So if you want the last element, you say A of -1, the last -1, A of -2. So you can count from both ends of these lists. So add up the first and last times 1/2, or if you like, the arithmetic mean of those two, right? The average of those two. Okay, so I write my function. It could be any function you like. I can tell NumPy to apply this function along. Now, when they talk about axes, think of it as, do you want to go along the rows? Do you want to go along the columns? Now, remember, this could be multidimensional. So if it's a 9-dimensional one, then you've got 9 axes. You can tell NumPy which direction you want to apply your function. So here, when I say the direction is 0, it's going to apply that function going down the columns. And when I say the direction is 1, it will apply it across the rows. So you can see, define a function, then just tell NumPy, go through this whole structure, applying that function to maybe the columns, maybe the arrays, or maybe it is axis number 12, or whichever one it is. So let's do a quick check. This is the original one. So I printed array 1. That's what's going on over there. Now, if I find the average going column-wise, you can see 0 plus 16 over 2, that's 8. Let's check another one. 4 plus 20 is 24. Divide by 2 is 12. The last one, 7 and 23 is 30. Divide by 2, you've got 15. But then I can decide to go sideways, row-wise. So 0 and 7, divide by 2, 3.5. Let's do the last one. 16 and 23, that is what? That is 33 and 6, 39. Then divided by 2, you've got your 19.5. Okay, so you can see what I'm talking about when I say it makes the coding easy, it makes it fast. Your time to have a program running is much quicker. You also get the statistical functions that you might need. So for instance, if I want the mean of array 1, axis equals 0 is going to mean that I'm going down the columns. Okay, so you've seen this one. If I change this to axis equal to 1, it means go the other direction, and it can give me the means of those axes, the numbers on those axes. Standard deviation, let me do this one just so that you can see that. Things like figuring out the standard deviation. Turns out that all the columns have the same standard deviation. That's because we just went 1, 2, 3, 4, 5. So statistical summaries, those are a breeze. Okay, so let me go back to the slide deck. What I hope I've convinced you here is that the NumPy array is not just any old array like you will find in other programming languages you might have learned. It is a structure together with a lot of the things that you would need when you're doing matrix algebra, vector analysis, and of course that is what a lot of your data science is about. Okay, so then the other one that I said is a big deal is pandas. And what pandas gives you is several structures, but the most important is the data frame. And the data frame is the closest you get to your relational database table-like structure, in the sense that you have columns, you have rows, and the columns all have the same type. So you can see in my little example, all the entries in this column are floating point numbers. All the entries in this column are integers, and so on. Okay, so this particular data set, by the way, is a data set on diabetes, and the idea is if you could get some predictors, like how many pregnancies the person has had, some measurements to do with the plasma, diastolic heart pressure, blood pressure, the thickness of the skin around the triceps, and all these other things, insulin, BMI, age, and then this would be the column that we're trying to predict, to see whether or not this person actually became sick. So the NumPy array is same type throughout and a lot of linear algebra. The pandas data frame is same type as you go down the columns, and there's a lot of data manipulation type functions that come with the pandas data frame. Now, under the hood, pandas actually use, the pandas data frame actually uses NumPy to do a lot of the array-like manipulations, as you would expect. So just to give you a feel for how pandas works, let me run for you a file I created. This one can go away. I created a little file to show you a bit of how pandas works. Here we go. Notice the two imports. I'm importing pandas, but I'm also importing NumPy. So the two actually work together very well. So let's do that. And then I want to read a file from my Google Drive. So this next cell that you're seeing, you won't need it if you do a similar thing on your laptop, because of course you do have permission to read from your laptop. This is just so that Google knows it isn't some strange fellow trying to read my data. So let me do this. What it does is it asks me to go get permission from myself. So I'll go give myself permission to read a file on my drive. So there you go, use that account. And it gives me a little security token, which I will pick up, and I'll go back over here and I will paste in here. Okay, so that little thingamajig, that's just if you're in Google Colab and you want to read from your hard drive. Now you can also read from the internet in Google Colab, so that's another way to do it. Okay, so you can see it has mounted my drive. All right, so my little pandas data frame, these are going to be the column headers. Notice that the NumPy one didn't have column headers because it doesn't try to behave like a database table. The pandas one does have column headers. And then I'm going to read a CSV file. That's just where the CSV file is. Once you've got your data frame, you have methods that are reminiscent of the Linux world, things like head and tail. Let's actually take a look at the head of this thing. Okay, so there's the head of my data frame, and you can see I have 1, 2, 3, 4, 5, 6, 7, 8 columns, and then the 9th one is the one that I would like to predict. So think of this as historical data, whether or not people ended up needing intervention for diabetes. Okay, so what can we do with this? You might want to know the shape of the data, how many rows, how many columns. Well, there's 768 rows. There are 9 columns. You can get basic statistical information. There is a catch-all method called describe, which, if I run it for you, describes your data set. So what's it giving us? The count, 768, we knew that. But the mean, standard deviation, the minimum, the first quartile, the 25% point, the median, third quartile, 75% point, the maximum for each of the different columns. Now, sometimes you have things sideways. You can change by saying axis equals 0, axis equals 1, make it go sideways or go up and down. Okay, so some of these entries you'll notice are a little suspicious. For instance, the minimum for the plasma measurement is 0. The minimum blood pressure diastolic is 0. You're not going to get any patients coming in with a 0 blood pressure The skin on their triceps is 0 thickness. They have absolutely no insulin in them. BMI, body mass index of 0. That I wish I had, but I don't. The others I don't wish I had. But that tells us something's not quite okay, and what's going on is the missing entries are in there as zeros. So not all the records are complete. Well, let's go take a look. Take a look at the first 20 lines. So look at the head 20. And yeah, you'll notice there's quite a few zeros, right? There's a 0. There's a bunch of zeros, right? Okay, so we've got issues with missing data. The columns where zeros absolutely make no sense, plasma, diastolic, triceps, insulin, BMI. Pandas allows us to cherry pick the columns we want to talk about. So I can just say, create me a new data frame called DF suspicious, and it is composed of these columns of the original data frame, which I called DF. By the way, in Colab, when you just type a variable, it will print it out for you. So if I do this, I'll get a thinner data frame with just the suspicious columns. Okay, so how many zero entries do we have in there? If you were doing it in standard languages, what you would do is you'd have a loop go through all the rows, and for each row go through all the columns, hunting for the zeros. In other words, you'd have a double loop, and then you would keep adding up the zeros, and you'd have to keep remembering that I need to add up the zeros in column 1, column 2, column 3, column 4, column 5. With Python, it's a one-liner. DF suspicious equals 0. This thing comes out as true or false. When you say sum, what Python will do is it treats the trues as 1s and the falses as 0s. And since you gave it a data frame, it will sum by column. If you wanted to sum by row, you put in axis equals 1. So if I do this, just that one line did what would have needed a double loop. It comes back and tells me you've got 5 zeros in the plasma column, 35 in the diastolic column, 227 in the triceps column, and so on. Okay, now I want to deal with those missing entries. So let's first change those zeros to true and falses, because remember I said when you have trues and falses, then Python can treat them as zeros and ones. We shall be able to better keep track of the trues and falses. So notice again, it's one line, right? Normally you'd have, again, a loop through each row, and for each row, go through all the columns, changing the ones that are absent, the zeros, into falses, and the ones that are, actually the zeros are becoming trues, and the others into falses. So that single line does this for me. And what has happened is, remember we had a few zeros in these positions. They've now become my trues. Okay, let's then decide what to do with them. One thing you could do is to use a special value, NaN, for not a number, and some algorithms can handle data that contains NaNs. So for instance, when you ask for the mean of 4 numbers and one of them is an NaN, what Python will do is to use the 3 that are available, add those up, divide by 3, and say here's the mean of the ones that you have. The NaN doesn't stop it from doing that. So let's try that. Okay, so we're not going to do a double loop and run through looking for the zeros. All we do is take my data frame, columns, plasma, diastolic, triceps, insulin, BMI, set them equal to, now take the same columns except dot, replace every instance of 0 with numpy's NaN. So that single line of code is essentially the same as a double loop going and checking where the zeros are and replacing with NaNs. Let's run it. Okay, so it's done. Let's take a look at the head. And what you have now is you have NaNs in those places where we have the zeros. Now, many methods will be able to run with that. Let's check just for sanity that we have as many NaNs as we had zeros before, because remember, that's the path we took. So let's try that. Okay, so pregnancies, none. Plasma, 5. How many zeros did we have? Plasma, 5. Let's take a look at insulin, 374. 374, 374, 374. Insulin, 374. So you can see what we've done is to replace those zeros with NaNs. Let's try the describe one more time. So describe. Okay, notice when we look at the minimum, these are the ones that bothered us. But now we've got things that make a lot more sense. There's your minimum. Now also the other numbers, some of them will change. Let's take a look at the mean. You see the mean of triceps, 29.153. Okay, let's go for the mean of triceps up here. Mean of triceps is 20.56 and so on. What's going on is those zeros were dragging down the mean to 20.5, whereas actually it should have been 24 point whatever it is down here. 29 actually, 29.153. Remember, triceps had a lot of, it had 227. So not only the minimum, but some of the other numbers are now more rational because we have taken care of the missing entries in the various records. Okay, so what shall we do with this now? Let's try running a little model that will try to predict that final column, the 8th column, based on the first 7. And I'm going to use a built-in, so Python has a lot of built-in models called linear discriminant analysis. This is coming from scikit-learn. As I told you, SciPy and scikit-learn have a lot of the data science kind of algorithms. Just so that you know what we're doing, we shall talk more about these things in the next seminar. But when you think of k-fold cross-validation, what it means is you're going to have your data set, and then you use a fraction of it for training and the rest of it for testing, and then you use a different fraction for training and a different fraction for testing. So you kind of recycle the same data, but with different roles for the different records. So that's what we're going to do. Let's bring these guys in. And this is where I'm building my model. So just again, so you know what's going on, we shall talk more about these next time. The predictors, that is the X, are going to be take all rows, that's what that column thing means, and columns 0 through 8. Remember, when you do that slice, it doesn't include the last number. So that's really 0, 1, 2, 3, 4, 5, 6, 7. And then the thing you're trying to predict, the target, that's going to be just column 8. Okay, so we make an instance of our model object, and we're going to do a k-fold with 3 splits. That means it will first try using 2/3 for training and the last 1/3 for testing. Then use the outer 1/3 for training and the middle 1/3 for testing. Then use the later 2/3 for training and the first third for testing. And then it will take the average. So down here, when we say result.mean, it is taking the arithmetic mean of the score. Scoring is accuracy. Python gives you many different ways of evaluating your models. That's a story for another day. But let's try to run this just to see, does it work at all with our NaNs in there? Okay, so let's go for it. And it spits out a whole bunch of errors. In particular, notice it keeps saying input contains NaN. The reason is that this model doesn't tolerate NaNs. So some operations will tolerate NaNs. Some operations demand that the records not have missing entries. Okay, so strategy 1 did give us the descriptions and so on, the statistical summaries. It didn't get our model to run. So here's strategy 2. why not throw away the rows that have missing entries? And there's a nice function in pandas, drop NA, drop the ones that have NAs in them. So the first two lines of this code are the same ones. Read that file that I read and replace the missing entries with NANs. And what I'll do, these three lines are the ones that are important to us. I'm going to show you the shape of the original pandas data frame. Then I'm going to drop NA. In place equals true just means don't create a brand new data frame, just drop the ones in this data frame. Then I'll print the shape of the new one. So let's go for it. And notice the drop NA would have been another double loop to go through my array to find the NAs. Well, notice we've got 768 rows at the beginning. We threw out the ones that had missing entries. We've got close to 400. So we've thrown away about 170 rows or so, which is quite a bunch, isn't it? But now we've got a data frame with every entry is present. So let's try training the very same model. So this is exactly the same code, and it does run. The accuracy is 0.7858. Let's take 78.6% accuracy. So we've got ourselves a model, but here's an issue with this model. Remember that when you get fresh data in production, you need to pre-process it exactly the way that you pre-process the data that was used to train the model. Well, our approach was to throw away any entry that didn't have all the values in there. So a patient comes in and we don't have one of the values. Well, then I can't do the same thing I did in training, because that would mean I throw away that record. So this model is great for records that are complete. It is not good at records that have any missing entries. Okay, so strategy 2, some success, but it does have issues. Here's strategy 3. What if I decide I'm going to impute, by impute we mean we plug in representative values in the places where there is missing data. So we have a function, fill NA, and you can decide to fill the NAs with whatever you like. A common thing is to use the mean of what you have as a representative of what you think would have been there. Other people might try more fancy things like do a linear regression and try to predict what the missing value would be. Let's just go easy and use a mean. So the first two lines, same as before, read the file, replace the zeros with NANs. Now over here, I'm going to print you the original shape. I'll fill the NAs with the mean. So notice just this line is the same as loop through all the rows and all the columns, and whenever you find an NA, now find the mean of the numbers in that column that are not NAs and plug it in there. It's a one-liner. And we've got all of our rows left, except of course the NAs have been replaced with the means. Okay, now let's try running our model one more time, and you will notice that this time the accuracy is not as high, but this model does work even if I have missing entries in some of the records, because we would replace those missing entries with the mean, and voila, we would have done exactly the same thing with the data in production as we did in training. So the accuracy has gone down a little. It is now 76.7. The other one was 78 point something. What was it? It was, here it is, 78.6. Okay, so we've lost a bit of accuracy, but we have a more general purpose model. Okay, let me tell you about a couple more things in the last few minutes. Visualization, we've got plenty of libraries in the Python world. In particular, Matplotlib is a very powerful library, sometimes more powerful than you want to be bothered with when you're doing the original visualizations where you don't mind to have a pretty basic sketch. Matplotlib might be overkill. When you're doing the final presentations and you care about fonts and shades of color and so on, Matplotlib is great. And there's a whole bunch of others. Let me mention a few like Bokeh, which has essentially more interaction. The user can pan and zoom in and zoom out and so on. Geoplotlib has the ability to give you a background map, and you put your geodata on that background map. So there are many packages that do the visualization you'll need. And there's another nice library, Beautiful Soup, and what it does is it allows you to fetch data from a website and process it to pick out whatever you need for your processing. So any of you who've had to pull down data from a website and have to parse it using a SAX parser or a DOM parser, and you eventually get busy with document get node by pattern and so on, it's much more pleasant. So it saves you a lot of work to get the data you want. Essentially, you do things like go to your website and get the data, the raw HTML, and you can say find all the tags that are table tags, and it will give you all of them. And here it is telling me that there's just 10 of them. Let me show you a little bit of Beautiful Soup before I round off the hour. And here is my document with Beautiful Soup. Okay, and from BS4 is Beautiful Soup version 4. So let me bring those in. This time, rather than go to my hard drive or to my Google Drive, we're going to a website. The website looks like this. It's at Wikipedia, and it has a nice big table with 3 subtables in there. And notice they have a heading for each one. These tables actually show the GDP for different countries, and the 3 subtables represent the different places they got the data from: IMF, World Bank, UN, and so on. So imagine you had to get that data and create a pandas data frame for your processing. Well, I'll just show you what the code looks like. So notice I say find all the table tags. I can say find the table tag that has class Wikitable. I can say find me the table row tags so that I can get those headers. I can grab the actual data, right? So here's where I get the 3 subtables. I can take a look at all the DTs, and I can find the table tags and assign them to different subtables, getting the names, the World Bank, IMF, and so on, getting the headers. So just by using straightforward methods of Beautiful Soup, I can end up creating a pandas data frame. Let me actually run this stuff for you just so that you can see how it works. So I want to run everything that is before this. And what I want to show you is, see, it has grabbed all the data that was in that website, and I can create a pandas data frame. Once I get to that point, then I can do my processing. And of course, I will do the same thing for the other 2 tables. This is same as above. I can do the same thing for the other 2 tables. Okay, so let me round this off by saying the majority of your time as a data scientist is spent gathering and preparing data. And what Python does for you is to give you the basic functionality you need for linear algebra, for statistics, for differential equations, for visualization, AI algorithms. So it gives you the tools you need, and it is not shy about using other languages to scale and to get the speed that it wants. Okay, so I hope that I've persuaded you to at least give Python a look. We do have courses at Learning Tree. If you look at our catalog in particular, course 1273 is about data wrangling with Python in particular. We also have courses on Python and Jupyter. Jupyter is an interface very much like the one I showed you on Google Colab. There are a lot of courses on machine learning, on big data. A good place to start exploring would be at this URL. This is where we have our data science catalog. And of course, I would very much like you to come back and see us and view some more of our webinars. So thanks very much for coming in, and let me turn it back to Amy for questions.
Hi, thank you for staying with us. If you have any questions, please type them in the chat pod, and we'd be happy to answer them. Okay, so we have one asking how long does it take to become a data scientist?
That is going to be a continuing thing. So to give you an extreme example, I first came across data science when one of my advisors, when you do your PhD, you need somebody from another department. There was a fellow in engineering, and he taught me symbolic manipulation. I've been learning ever since, and every day I have to read up on what people are doing. So think of it as I'm going to become a professional student. I'll forever be learning new things, but as I go along, I will be practicing the ones that I know, at the same time learning new things. And each and every problem you solve will have its own little twist that will make you sit back and think, okay, how does this one work? Try out different things. So it is an ongoing process. I would say, of course, it depends on your starting point. You need to be able to code enough to represent your ideas in code and see them run. You need to understand the business you're in. So for instance, if I was to go into a financial company, I would have to learn what do they think is important. So you have to know what is important so that your questions are good. Some people will already have that part of it. And then you learn as much statistics, as much linear algebra as you possibly can, because even when we're protected from getting our hands dirty with that stuff, we need to understand what it is doing and know what the tool is doing for us. So think of it as you start now and you just keep at it on and on and on, and you get better and better and better.
All right, our next question is, which is the most easy to use IDE to work with Python?
For that one, first a disclaimer, I will be biased because of course the ones I use are the ones I like. So when you're starting out, if you are going to be a user, so you're going to be programming the stuff, then the one I showed you, just having your Google Drive and you just open a file as Colab, you're ready to type. That's like the fastest way you can get in, and it gives you a really nice interface, as you saw, that you can use to experiment. I would do something like that initially. Then when you decide you're going to set it up on your own laptop, get a kind of all-around framework, something like Anaconda. I use Anaconda because for the same interface, you can actually do some R, you can do some Python, and it is becoming very, very popular. You can do something called Jupyter. Jupyter is a very nice interface. It looks a bit like the one we saw, and more people are going towards Jupyter. So I am biased towards the Jupyter side. There are others like Spider, which do have a following. So it's not so much that I think it is not a good one. I'm just really exposing my bias towards Jupyter.
Okay, the next question is, can you use pandas with the CUDA framework?
I have seen commercial, and I swear I could have seen an open source. The answer is yes, but who's doing it? Essentially, I've seen people who are wanting to use their video cards to get more performance. I wish I could remember in my head where it was, but the answer to your question, Mark, is yes. But it's kind of a roundabout thing. You have to install something and then you're ready to go. I wish I could remember exactly who had it.
And for our last question is, will we be able to access the webinar later on? The answer is yes. You will have access to it through My Learning Tree.
Yes, in your My Learning Tree account. Mm-hmm. Now, I don't know about the timing. Do you know the timing, Amy?
No, I believe probably.
Andrew wrote in the Andrew wrote in the chat box that is by the end of the week.
Okay. And actually, we have another question. How do I get the Google environment you were using?
As long as you have a Google Drive account, you've got it. So essentially, when I go to my Google Drive account and I try to open a file, I'll just right click here and I can say Google Colab, and there I am. So as long as you have a Google Drive account, you have it. That's why I was recommending it as the fastest way to get started, because it is a do nothing thing. Just go and start.
Okay, well, that seems to be the last question we have. If you have any more questions, please put them in the chat pod. Otherwise, thank you so much, Chris, for your time and, effort on this webinar.
Well, thanks very much, everybody, for attending. And I hope that I have planted a seed that will flourish as you take your Python journey. And do look at our catalog to see the courses that might be suitable for your purposes. So thanks very much.